the joint AEP, which is the secret not only for channel capacity theorem, but for the multiple access channel, achievable rate region, for the Slepian-Wolf, simultaneous data compression region, for essentially much of multi-user theory. We'll use it to give a proof, like a 15-minute proof of Shannon's theorem. I guess it's more than 15 minutes. So we'll prove the achievability and the converse. Okay, now for some properties of C. All right. C. All right. 1. Capacity is always greater than or equal to 0. Or, if you will, 2 to the C is greater than or equal to 1. The number of noise-free symbols is always at least 1. Right. Proof? I, mutual information is greater than or equal to 0, and C is max of I over P of X. So that's a triviality. 2, the capacity of a channel with, I will use this to designate the cardinality of script X. Script X is the alphabet for X, and this symbol denotes the number of symbols in X. Right? So the statement is C is less than or equal to something. All right? I of xy, I haven't put that in yet. I of xy is h of y minus h of y given x. So the entropy of y is less than or equal to the log of the number of elements in y. And this is greater than or equal to 0, so minus it is less than or equal to 0. So you get C is less than or equal to log y. You can't get more bits through the channel than you can get bits in y. Y takes on 8 values. You can get them, there are most 3 bits. You know, the log of 8 is 3. There are most 3 bits you can get through such a channel, because even if you could affect y perfectly, that's the most you could get through. And then, of course, I of xy is equal to h of x minus h of x given y. And this is less than log of the number of inputs. Obviously, you can't get more through than you can put in. And this is greater than or equal to 0, so minus it is less than or equal to 0, and so on. So we now have log x. And since this is less than each of them, it's less than the minimum of them. So it's nice to know that our formula is looking good. What we'd really like to know is whether our formula means what we think it means. All right. So now, C for a symmetric channel. What's a symmetric channel? It has rows P1, P2, through P sub m, and the rows are permutations of each other, and the columns are permutations of each other. Actually, you just need, well, for example, you might have all cyclic permutations of the top row. So let's be lazy. I won't define what a symmetric channel is. But let's look at the mutual information for a symmetric channel. It's the entropy of y minus the entropy of y given x. Now look, the entropy, if I put in x and I get out y according to this distribution, then the entropy of y given x is just h of the generic p. Because no matter what x is, we have the same probability masses in y. So h of y given x is h of p. Now h of y is less than or equal to log y. That is log of the number of elements in y, with equal if y is uniform, i.e. if x is uniform. And so in order for us to be able to induce a distribution that's uniform on y, you need to have the ability, well, it would be nice if every column were a permutation of another column. Not all permutations, but just, so if it's a symmetric channel, which I got lazy on, then we have this, and the capacity then is log y minus h of p. Right? So here's an example. The channel transition matrix is a half, a half, a half, and then a fourth everywhere else. Halves on the diagonal, fourths everywhere else. Okay, h of y given x, so I is h of y minus h of y given x. H of y given x is always the entropy of a half, a fourth, and that's 3/2 bits. And h of y, by putting a third here, you can induce a distribution of a third here. And so this, I'll put a less than or equal, is log of 3. So C equals log 3 minus 3/2. That's nice. All right. And let's look at another example, the random typewriter that is telling you what's going on. Here's 1, 2 through M, and I'm going to have outputs here, and for every input I'm going to have equal probability on the outputs. I'm going to have T possible outputs. And now I ask you, what's the capacity of that channel? Does it depend on M, S, and T? And, oh, it's a symmetric channel, by the way, with these specifications. The answer is it only depends on 2 of them. It depends on S and on T, but not on M. So, C is equal to log of y minus h of y given x. But the conditional distribution is uniform over S possibilities. So this is log S, log S. And this is log y. Well, I said there were T possibilities here. So this is log T. So C is equal to log T over S. The number of output variables, symbols, divided by the number of symbols in each fan. Again, that fits nicely. And if we substitute for T, h of 2 to the h of y, and for S, 2 to the h of y given x, we get 2 to the I here, log of 2 to the I is I, and we get the answer. So everything's working out for the formula. I haven't yet proved that the formula, max of I of xy, is the answer to the question. So the real question is what's the question? You know. By the way, that's how we often have answers, and you're trying to find the question for which it's the answer. That's why entropy plays such an important role in our thinking, both in thermodynamics, statistical mechanics, and in information theory and data compression. It's the answer to about 6 different questions. And some of the questions are really different.